Thank you for the introduction, and hello everyone. Thanks for joining this session. Today I'm really excited to share with all of you some of the strategies that have helped me to collect better labels while training machine learning models and basically giving the model what it wants and needs. So let's dive in. Let's say that we have a machine learning model that we want to train. So in order to train this model, we need to give some data as insights so that we get the knowledge as an output that we wish to get. So now let's say it's not a machine learning model. Let's say that it's actually a person. It's a child that is learning a new task or an adult that is learning, let's say, a new language. In all of these cases, whether it's a person or a model, we need to give some insights, some data, so that we get the output. And of course, the more data that we give as insights to the model or the person, the better output we will get. So let's say that I'm trying to learn Portuguese, so of course, the bigger vocabulary and grammar that I'm exposed to, the more likely that I will be able to form sentences and start potentially, hopefully, speaking Portuguese. But what if majority of this information is redundant or too similar? Let's say that in the example that I'm trying to learn Portuguese, if you tell me how to say hello in 5 different ways, I will be great in saying hello in many different ways, but I still will not be able to order anything at a restaurant, for example. And the same applies to machine learning models, right? If we give too similar or too redundant information to the models, even if they're in large quantities, it will not really yield the output that we wish. And this is actually going to be the foundation of my talk today, where I want to focus on the fact that in some cases in machine learning model training, quality matters more than quantity. So let's now do a small recap of supervised learning approach. So we typically, of course, start with unlabeled data, which we then need to get annotated by human experts so that we end up with annotated data, in this case, the usual example of images of cats and dogs. We then feed this data to the machine learning model, and then once the model is trained, we need to basically get the predictions that we go for. So in this case, when we ask the model to tell us, is this a cat or a dog, the model will output correctly that it's a cat. And in this particular flow, of course, in this part, the more useful data that we give to the model, the better it will be. But when we say labeled data, we mean that we need to have humans involved in the loop, and these are experts that are familiar with the domain knowledge. And this already introduces some challenges when we need to have humans in this loop. And the challenges of manual machine learning labeling are, first of all, that getting labels is quite costly. So if we have a data set of 1 million labels, of course, ideally, we would want all of this data to get labeled. But in real-life scenarios, we cannot get this because it's quite costly and it takes time. So our stakeholders or our manager might ask us to basically, given the time and the budget that we have, that will translate that we can actually get 100,000 records to be labeled. Okay, then let's assume that our assumption is that with 100,000 labels, we can get the output that we want. Now the second challenge comes in. How do we actually know which of these 1 million records to select? How do we know which 100,000 labels are going to be yielding the most information and will improve the model performance? And this actually is where active learning comes in. So to solve these two challenges is where we can use active learning, which is basically an idea and a technique in machine learning model training, which lies under the assumption that if we give the model the chance to choose what data needs to be labeled, the model will be able to perform better with less training. And then the process would look something like this. So we start with unlabeled data. We get this data annotated with humans. We end up with the labeled data which we feed to the model. And then this is where actually active learning comes in. Once we have an initial model on which we can apply this strategy, we need to think of two specific things. So when we talk about active learning, we're talking about the sampling strategy first. So how does this process look like? In this simple graph, we see where it comes in, but how does this actually look when we go one step deeper? And secondly, we have to think of query strategies. So how do we ask the model to choose what it wants? So let's start with the first part. The sampling strategies, so how to collect these instances using active learning. The first strategy out of 3 is called stream-based selective sampling. This is also known as sequential-based sampling, which means that we first, of course, get some training in the model, and then once we have the first version of the model, we will be asking the model to evaluate a new unseen instance, whether a new unseen instance will actually be useful for the learning process. Now, if the model believes, based on the learning so far, that this instance is going to be useful, we will ask for human annotation on it, but if it's not going to be useful for the model, we will discard it. And this particular approach is useful when we have real-time data analysis or streaming type of data, such as video streaming in production, and the data is incoming basically on a daily or even like in a stream-based fashion. So in this case, we will be retraining the model quite often, and this is particularly useful for solutions in production when we want to improve the model performance and we want to do multiple retraining iterations. A second approach, quite similar to the first one, yet different, is the pool-based sampling. In this case, the process starts similar, but then the active learner is going to actually be selecting the top n informative instances out of the pool of unlabeled data. This approach lies under the assumption that we do have a pool of unlabeled data available from which the active learner can select instances from. And this is also quite useful when we have batch processing, so when we're not really expecting to be processing and improving the model on the go. So we can use this in offline model training or when we have retraining in a period of time. And in this case, we will be retraining the model again in iterations, but then less iterations than in the first one. The third strategy is called query synthesis sampling. This one is a bit more complex, it's quite different, because here the active learner will not be selecting or choosing from any instances, but it will be actually generating these new instances for us. Now, this is useful if we don't have actually any unlabeled pool, so we have to be generating this data, or if the data that we have are not that useful. So if the cost for getting human annotation is quite high, we want to here optimize that with the least amount of labels, we get maximum learning for the model. So then we apply these strategies where we generate the instances. So if we do a small recap, just visually to see all of these three in parallel, we see that we always start from the unlabeled pool of samples. In the stream-based selective sampling, we are getting one instance at a time in a sequence fashion, and then the active learner decides if something is going to be useful or not. In the second approach, pool-based sampling, we're actually going to be asking the learner to select top n instances from the unlabeled pool of data. And then lastly, in the third one, the active learner will be generating these instances that need to be labeled for us. So for the remaining of today's slides, let's focus on the pool-based sampling strategy. This is one of the most commonly used ones and quite easy to understand and showcase on slides, so let's stick to this one for now. Here, as you already see, we have the active learner that I kept mentioning. So, okay, the active learner selects in pool-based fashion, but how does the active learner actually select these instances? This is also known as query strategies. And there are many query strategies available. I will just name a few now to just give you an idea of how it can look like and just showcase one of the simplest ones. So let's say that we have initially pre-trained models and we want to run predictions on these three instances, which are unlabeled, and we want to select one most informative instance for the next iteration. So if the model is predicting whether it's cat, dog, or bird, and in this table you can see the predictions as outputs of the model. So the first and one of the simplest strategies in active learning is called uncertainty sampling. So in this strategy, we will be selecting the top predictions from every instance and then selecting the minimum out of those. In this case, for first instance, the model is certain with 0.8 that it's a dog. In the second one, its highest prediction is that it's a dog again, but now with 0.5. In the third one, that it is a cat with 0.55. So in this case, we take these three and we select the lowest one, which in this case is 0.5, which means we will be labeling instance number 2. Another slightly improved version of this is the margin sampling strategy. This strategy means that we're taking the top 2 predictions from each instance and we're doing a subtraction of the 2. So in the first one, actually in all 3 instances, the model is, the top 2 highest probabilities are between cat and dog. So when we do basically the calculation, we see that in the third instance, the model is most uncertain whether it's a cat or a dog. That is the lowest, which is 0.1, the difference between the 2. So that means that with this strategy, we will be selecting instance number 3. And also, when you think about it practically, this translates that the model cannot distinguish clearly, is this a cat or a dog? It's maybe blurry or a fuzzy image, so maybe these animals look too similar in this case. So by giving more of these labels back to the model, next time the model will be clearly distinguishing in this type of image setup that it is cat or dog. Another example strategy is called entropy sampling. And in this case, we're calculating the entropy for every instance, and then we were selecting the one with the highest entropy, which again, in this case, it will be instance number 2. So these examples that I've shown just now are when we have a single model that is doing the predictions for us. But what if our approach involves multiple models, or we want to actually be able to do a bit more diverse sampling? Then we can use, for example, one strategy that is called query by committee. In this strategy, we're not using one model's predictions, but a few. Let's say we still have these 3 instances that I was talking about, but now instead of one model, we're running 3 models in parallel. And then one idea here could be that we're selecting by disagreement. So where all of the 3 models disagreed, let's select that instance to be labeled. You can even think that in some cases, if you think that the model is biased, you can even select instances where the model is yielding the same output, because then you might also remove this bias if the model is way too certain in all 3 models that it's indeed some prediction for one of the labels. So now that we've understood or went over the sampling strategies and the query strategies, how do we make that decision? Let's think, how can this play out in a real scenario? So let's say that we're just starting with a solution or a project requirement in our team and organization, and you may already be thinking that of some solution or a project that you have in your day-to-day environment that requires manual labeling, and you struggle with this task. So let's say that we have a tight deadline. Maybe it's a proof of concept, maybe it's a go-live date that we have a strict timeline for. Let's say that for this task and for this solution, we need expert annotators. So it cannot be anyone, but it needs to be someone that is quite trained and basically familiar with the niche problem that we're trying to solve. So this person can really annotate and label the data for us. Let's assume that we don't have any data available, as in most cases, and there's no data available within your organization or online. And luckily, we have records to choose from. So we do have an unlabeled pool of data. Now, having this in mind, if we need to start the project, we start with the unlabeled data part. So I previously mentioned we need to get started with the learning process, but how can we get started if we don't have any data? So the first iteration is without active learning. Something that I have applied is either random sampling, so you can just, for the first iteration, just to kickstart the learning process, you can select randomly some samples from the unlabeled pool of data. But if the prevalence of your true positive class is quite low, and if you select randomly, chances are you just get negative samples in binary classification, for example, then you might apply something a bit more advanced but very simple, such as keyword-based approach. So if you're dealing with text-based data, something that have helped me is that for the first iteration, I'm using some keywords to get a mix of the 2 classes so that I get some representation for the beginning. Then we feed this data to the machine learning model. And then active learning loop comes in. Now that the model has some knowledge, we can apply active learning strategy. Let's say we stick with the pool-based approach with uncertainty sampling. So the active learning approach here will be actually taking the data from the unlabeled pool and the learning so far to select the top most informative instances, which need to be annotated, and then we feed this back to the labeled data and we repeat the training process. We then, of course, do the model evaluation, and most likely, after one iteration, we will still not be getting the results we want. So we need to repeat this process a few times, either until we have exhausted the resources that we have available, or until we have hit the performance of the model that we go for, and we've hit the metrics, and we call it a success. So this is how the process would look like from start to actually doing a few iterations of active learning. But how does it actually look like in practice in code? So there are good news for this as well. There is a package that I have used in my career so far that is quite easy to get started with, and you can already run active learning iterations with just a few lines of code. This is an open source package called Modal. And basically, by initializing the active learner from this package, we need to pass an estimator, which is actually the model that we're training with. So this can be a simple random forest model, it can be a neural net, or even a pipeline if you're dealing with an ensemble of models, or you have a pipeline running to do the predictions and inference. Then we need to pass as well the query strategy. And in this case, we just used the off-the-shelf query strategy called uncertainty sampling as before. And you can choose a lot of the available query strategies from this package, but you can also decide to actually implement a custom strategy based on your use case and problem if you wish to do something more advanced, also depending on the data if you're using tabular, image, or text data. And then you pass this function here. Then we need to pass the initial data for the training of the model. This is the randomly selected or the keyword-based selected samples to get started the training. And once we have done this, we need to do the querying. So with a simple line of learner.query on the unlabeled pool of instances, we can already select the top n most informative instances. In this case, we set n to be 1,000, let's say, for example. So this, using the uncertainty sampling strategy and the model that we just specified, the active learner will select 1,000 most informative instances for us. We then need to give, of course, this data to be human annotated. And then once we get back the data, we will feed this data back to the learner. So with learner.teach, we're going to reteach the model with the new information that we have just collected. And with this, we have completed one active learning basically loop for now. In most cases, as I mentioned, we would like to do multiple of these iterations over a longer or shorter period of time. So you can set up a process for this to actually run this to maximize the learning for your model in multiple iterations. And now, by giving the model what it wants, we have actually learned and proved that it can learn about mistakes and gain knowledge where the model is most uncertain about. Two similar labels will not be annotated twice. And all of this is actually leading to the fact that we will be reducing the costs needed for achieving the same results. And here, when I mean costs, when I say costs, I'm referring to the time it takes, of course, to complete the model training, also the cost for human annotation, but also the computational cost of the model that we're running, because we will be performing the training with way less data, which is going to be most useful. That was all from my side. Thanks a lot for the attention. And yeah, now we have some time for questions. And also, I just want to mention that I will be around after this talk. So if you have some more questions that we cannot get answered now, or if you also have some ideas or strategies that you have applied, I will be really curious to learn from you as well. Thank you.